So, hello everyone. Welcome back to the course. So today I will just be talking about superconductivity. That's the topic for today. So today we talk about superconductivity. Next week there are no classes, so there will be a gap next week, and we will go back over the next week, and then we will have topological classification and topological superconductivity. So I will give a colloquium tomorrow about topological superconductivity, but we will have more details in the class that we covered the next week, okay? Okay, so that is the idea for today. Probably not all of this. We will see how far we go. So the first thing is just a brief introduction to superconductivity. Then we will see how phonon interaction can actually lead to some effective, attractive interaction that will compete with the Coulomb repulsion between electrons. So then the basics of the BCS theory of conventional superconductors. So we go more or less in, with some technical details how to go into the equation, the BCS equation for the superconductor. Then the value of the Yen approximation. This is an approximation that you get from the BCS, and it's useful in the case in which you have a system which are non-homogeneous, meaning the fields may be position dependent, the pairing of the electron may also be position dependent, and so on. Then we will have an overview of Josephson junctions. What are these Josephson junctions and what they are useful for? Eventually a little bit of quantum computing. Superconducting Q is built with Josephson junction. Maybe I will talk a little bit about that. And then a couple of very particular things that happen when you have interfaces between superconductors and non-superconductor elements. So you may have so-called Andreev reflection and Andreev bound states. So these Andreev bound states are particularly important because from there, the Majorana states that are useful for topological quantum computing are actually emerging from this Andreev bound state. But we will talk maybe more over the next week. So, superconductivity. Well, it's a very intriguing state of matter. So it was discovered in 1911 by Ones in the Netherlands, and he got actually the Nobel Prize in Physics in 1913 for this discovery. There are at least 10 Nobel Prizes related to superconductivity. So there are all these years are directly related to superconductivity, these couple of years indirectly, but there is also superconductivity in there. And I'm pretty sure that there will be other Nobel Prize related to superconductivity. So we still have a very big question, what are the mechanisms behind high TC superconductors? And if you have a theory that really works for that, or you discover a very large or high temperature superconductor, you will get Nobel Prize for sure. Okay. So what is the typical thing of these materials? So they have zero resistance. They expulse the magnetic field. So they can quantize, they can trap the flux, they can quantize the flux, magnetic flux. So they, as I mentioned before, if you put it in contact, superconductors in contact with a material that is non-superconducting, you may have this phenomenon that's called Andreev reflection, which is somehow the superconducting analog of Hawking radiation in black holes. So essentially what happens, you have a particle that is coming, and this particle is reflected like an antiparticle. In that case, particle is in Hall for the case of the superconductor, but in the case of Hawking radiation, it's just this. So we can observe microscopic quantum phenomena. So typically you want to observe quantum phenomena, you really have to go to atomic level, right? So atoms and so on. If you want to see quantum phenomena in superconductors, you don't have to go to such a small size. So even in microns, so you can make a device which is few microns of superconductor, and you can see quantum effects at this level. So it's perhaps the only system that you can see quantum effects really at the microscopic level. Then we have proximity effects. So this, you can have superconductivity. You put another material that is not superconducting. This superconductivity may leak. It can make the other material that you put superconductor or to get some superconducting properties. And this is a big game changer because for superconductivity we have some materials, but this is limited. So there's material that are superconductor that have specific properties. And we have another material like semiconductors or topological insulators or whatever you want. And these other materials have other properties. So when you combine them, you can get superconductivity in this material that have different properties, so you can have a plethora of different effects. Okay. So, well, and one of them, for example, is topological superconductivity. There is a candidate for topological superconductor, which are the P-wave superconductor. There is no P-wave superconductor in nature as long as we know. There are some candidates, but the TC is so small that it's very difficult to really check to prove that they are really P-wave superconductors. So, but you can engineer by doing this proximity effect. So you can get some interaction from one material, superconductivity from the other, and engineer this P-wave like superconductors. So then superconductivity have multiple applications, mainly magnetometry, sensors, digital circuits, particle detectors, superconducting electromagnets, magnetic levitation for trains, quantum computing, transmission power cables, etc. So if you look at this, at how the resistance, if the superconductor change with temperature, you will, and you compare what happened, the behavior with the case of metals. So in a perfectly metal, so you have zero resistance when T goes to zero. But there is no perfect metal, you always have impurities there. So the resistance is finite when you go to T equals zero, is this value here. And if you increase the temperature, they increase. So for the superconductor, as long as you are below certain temperature, which is called the critical temperature of the superconductor, the resistance is going to be zero. And it's going to jump to a finite value as you increase the temperature. As the temperature goes above Tc, the superconductivity is gone, so you have phase transition from superconductivity to whatever the metal, it could be a metal phase or whatever you have. And then the resistance starts to be finite here. So here is zero, between 0 and Tc, and then have a jump and start to increase with the temperature. So here is a table of this critical temperature, which is also very important for the superconductors. So you can see that the critical temperature in Kelvin. So the very first superconductors, so you can see here up to maybe 1980 something. So most of these superconductors have a critical temperature that is below 30 Kelvin. It's pretty small temperature, that's why you have to cool the system down. So a typical superconductor, let's say aluminum, is a very common superconductor, but you have to cool it down up to 4.2 Kelvin, which is the critical temperature for aluminum. So you have to put liquid helium to cool it down. And liquid helium is not cheap, so it's make application for this kind of material very difficult outside the lab. Now you can get high Tc superconductors, and when I say high Tc, this high is high in comparison with the other one, but this is still quite cold. So you see here, even the largest, let's say here is at 150 Kelvin, which is still quite cold, but then you can use liquid nitrogen, which is very cheap, and then you can cool down these superconductors. Now you can get even higher TCs, but then you have to apply a lot of pressure. So I think you can even get very close to room temperature TC, but with very, very high pressure, which then does not solve the problem, because then you have to apply these very high pressures.
Why do you need high pressure?
For these high TCs, I don't know. So there are some of them that when you apply high pressure, you get this superconducting phase. But this is a kind of superconductivity that is still not very well known. Okay, so the mechanism behind this superconductivity is not known. So there are some hypotheses, some theories. Okay.
From last 40 years, there is no improvement.
Sorry?
From last 40 years, there is not much improvement on superconductivity, high temperature.
Oh, this is just a table with a few of these elements, but there are many other elements in between. And I think right now, this is at 155 gigapascals. Okay, it's 200 Kelvin, which is is just not so cold. It's still cold for us, but not so cold. And is 155 gigapascals you have to apply. So it's a huge pressure. And you can go higher. I think the record is really close to room temperature, but also you have to put a lot of pressure.
But
yes.
in fact, there's been reports of some room temperature superconductors. Can you mention them?
There were some reports, I think.
This is in Iraq in 2025.
Well, I remember, I think a couple of years ago, there was a person in University of Rochester, Michigan, that was one of the first saying, okay, we have this superconductor at room temperature and so on. But as far as I know, there were a lot of problems with this paper. I think even there was some retraction, and there was some suspicion of scientific misconduct and data manipulated. And so the last ones, I don't know. Okay, so we'll see if. All right. So let's have, I will be talking about conventional superconductivity. So this high TC superconductivity, I won't talk about that. I will talk about conventional superconductivity, which is essentially this BCS superconductivity, which is something that nowadays we understand quite well, I would say. Okay? So I won't tell you about some theory that maybe is not true. So I will tell you a theory that it works, because we know that works. Okay? But it's just for this S wave for conventional superconductors. S wave or the wave, but I will talk more.
I marked all these superconducting materials. You can see
Okay,
it's
so let me.
actually quite common to be superconducting.
It's not.
Okay.
I will put this video here, and it will show you a little bit of animation on how this pairing, due to the electron-phonon interaction, comes out, and then we will see this in more details. But just to visualize the idea. Okay.
This periodic table, I marked all these superconducting materials. You can see it's actually quite common to be superconducting. Okay, so now we look into why there's no resistance. Let's go back to our conductor and observe just one electron in a superconductor has been cooled down by helium. So the thermal vibrations are negligible. As the electron is being pulled to the positive side of the battery, it flies in between atoms of the lattice. These atoms are positively charged because they have lost their electrons through the conduction. This means that the electron will cause a slight attraction of the atom, since it's negatively charged and the atoms are positively charged. If you have positive atoms clumped together in low disturbance, they are a bit more positive. Now, a new electron flying in will be attracted to this low disturbance because it is slightly more positively charged. You would probably expect, since slightly charged repel, these two negative electrons should repel each other, but they don't, because in reality, many more atoms in the lattice is actually a part of this disturbance. And the attraction happens over hundreds of thousands of that. The attraction causes these two electrons to go together and bind to what's called a Cooper pattern. But this bond is extremely weak, and even thermal vibration will break it. That's why we need the liquid helium. When two electrons go into a Cooper pair, something interesting happens. Protons, neutrons, and electrons are usually what's called a fermion particle. There's another type of particle called the boson. A boson is a boson. I'm not going into details about this, but being a fermion, like the electron, means that no two particles can be in the same state. That's why we see atoms like this. We have fermions, electrons orbiting the nucleus. If there were bosons instead, they would all go into the same state. So they would all clump into the ground state, and no chemical reaction could occur. But bosons can be in the same state. And that's of superconductivity. Because when two electrons go into a Cooper pair, they are still fermions, but they act together as a boson. That means all the Cooper pairs clump into the lowest individual, and they will all be in the same state, because they are bosons now and not fermions anymore. Now they can behave as one big group of particles in the same state, because the Cooper pairs are bounded over a big distance. All Cooper pairs become overlaps. This new big overlap becomes entangled and now behave as a large network of interactions. This network of interaction will be attracted to batteries postcode and therefore conduct. The collective behavior of all the electrons in that network and in the solid prevents any further collision with the lattice. If it were to rely on the network would just recombine into new Cooper pairs. To have resistance, the whole network will have to rely on the lattice, and that's just too uncertain to happen, so there is none. Another way to think of it is that current has to be resistant-less because you can't take any energy from a system that's already in its ground state, which these bosons are. So superconductivity is just a strange quantum dance of Cooper pairs, electrons, and vibration in the lattice. There is much more to a superconductor than just zero resistance. Let's first take a look at the magnetic properties. If we put a normal magnet here, the magnetic fields are often drawn like this. They represent the direction and the strength of the magnetic field. So if we have other magnets, they would certainly be affected by it and would align it to this field. If we have normal matter, like this little cylinder here, put next to a magnet, the magnetic field would just pass right through it, like nothing happened. But if we replace the cylinder with a superconductive cylinder, the cylinder will just repel the magnetic field. It will not have any magnetic field inside of it. This happens because the electrons inside the superconductor create small vertices that repels the magnetic field, kind of like really small electron coils. Now we're actually ready to create really fast levitating magnetic superconductor trains, because if we have a magnet up here, you can see the magnetic field, and we have a superconductor down below. The superconductor will not have the magnetic fields inside of it, so this will not have the superconductor repels the magnetic fields, and therefore the magnet levitates.
Okay, so this was a very brief overview, more or less, about superconductors. But let's get into a little bit more details about this effective phonon-mediated interaction that is attractive. So here are more or less the things that are relevant for this phonon-mediated attractive interaction. So first we have in the lattice we have ions and we have the electrons. So the ions are heavy in comparison with the electrons, and they move much slower than the electron. So when the electron comes and it's polarized, create this charge around. So the ions are attracted by the negative charge of the electron, so they go together. But they are doing this slow. So the electron may leave, and since they are still working, moving slower, so they get slower into this accumulation and give time for other electrons that are farther away to fill this extra accumulation of charge at a given point. So the other electron get attracted. Okay, so in other words, heavy ions are slow movers around their equilibrium positions compared to fast and light electrons. Therefore, dynamical local lattice distortions arising for electron-ion collisions remain long after the electron that caused them have passed. So a local distortion gives rise to a small dipole, a dipole moment, so this is this electric dipole moment, that can interact with electrons. As a result, another electron in the vicinity of the local lattice distortion can be drawn towards it long after the initial electron has left the scene. Okay, so again, so this actually is important that they have this different speed of motion, because otherwise, so if the ions were moving as fast as the electron, so they will create this dipole, but as soon as the electron just move away, this dipole will, they will just go back to the equilibrium position. And the other electron won't have time to feel the attraction of this, okay? So the other electron will feel the attraction of this because, well, the ions will take longer to get back to the equilibrium positions. So the disturbance is gonna last for a while there. Then as the electrons are far removed from each other, so the repulsive Coulomb interaction is reduced and the attractive effect from the local distortion can become dominant. So this can happen, of course, if the electrons are far away, because otherwise this Coulomb interaction repulsion is very strong. So what it means is that on average in time, you will like these two electrons to be as far away as possible. And this intuitively tell you that the best way to pair the electrons will be if the electrons have different momentum. Because if they are moving in the opposite direction, so the time that they are close to each other is going to be smaller than any other configuration, right? So if the electrons are moving in the same direction, so they can have a lot of time close to each other, and you won't have the pairing. So if they are moving in the opposite direction, so they just, there will be just a small amount of time they could be close, and they will be essentially at far distances. So when they are far distances, the Coulomb repulsion becomes smaller, and then this effect of the lattice attraction of the distortion can dominate over the Coulomb interaction, so you can essentially get effectively an attractive potential between the electrons that is mediated by the lattice. Okay, so that's essentially what is written here. The conclusion of this is that the best two particle states for the purposes of pairing is a state that have opposite K momenta. So I will go into more details in this, but this is more or less the idea. The other thing is the Pauli principle. So also the more for the attraction, so you want also there are two things. You want them to be far away because the Coulomb interaction becomes smaller, but you want the attraction also to pull them together, okay? Now, we know that for two fermions to be able to be pulled together, they will have to have which spin? Equal spins or opposite spins? So if I calculate the probability to find two fermions close to each other, and I calculate this probability for two fermions with same spin and two fermions with different spin, which one I will have a probability to find closer than different spin, right? Because then, so the Pauli principle don't tell you, okay, no problem, they have different spin. If they have equal spin, the Pauli principle tell you, okay, they don't want to be together, okay? So that is why also the most favorable pairing will be then for electron with opposite spin. So the conclusion of this analysis is that, well, the pairing will be favored if these two electrons have opposite spin and opposite momentum. Okay. All right, so what is the form of this electron-phonon interaction? I won't cover this in this lecture. It's rather complicated, rather technical, needs green functions and so on. I will need a couple of lectures maybe for that, so I will just give you the result, okay? But you can discuss, you can see every book of superconductivity, probably there is a chapter about this. Okay, but this is the result, okay? So we get here the Hamiltonian, this is written in second quantization. We have here the interaction, so the single particle part of energy of the Hamiltonian. So epsilon k is the single particle energy as a function of momentum k. And then we have this part which is the two-body interaction, this particle-particle interaction, that which amplitude is given by the Fourier transform of the potentials in real space. So you get the Coulomb potential in real space, you make the Fourier transform, you will get this part. And if you get the real space potential of this electron phonon or electron-electron interaction mediated by photons, you will get this expression here, okay? So this is what you need to calculate with these green functions and so on, but forget about that, so this is the result. is actually not so relevant for what I'm going to say. So what do we have here? Well, this MQ is essentially a matrix element that have inside the electron-phonon interaction, okay? So omega Q is the dispersion relation for the phonon, so it's the energy of the phonon as a function of Q, the momentum of the phonon. And then omega is the energy that is transferred during the scattering of electrons with these phonons, okay? So this is the potential, and if you plot this potential, it looks like this, okay? Now you see this total potential, which is the sum of this phonon-mediated potential and the Coulomb potential. It's in some, for some frequencies it's repulsive, but there are a region of frequencies in which it is attractive. As you can see, here is repulsive, so it's larger than 0. But here, between minus omega Q and omega Q, it becomes attractive. And actually, if this frequency is very close to omega Q, this is going to be very attractive, okay? Because, in principle, this goes to infinity. All right, so this is essentially the potential that that tell us if there are some materials and the phonons in this material, are such that you will have such a behavior of the effective potential in this region of frequencies, then this material can become superconductor. Now, because you see this region of energy transfer is very small, so in principle, compared to the Fermi energy of the materials, so the maximum omega Q is the maximum frequency of the phonons in the material, and it's called the Debye frequency. So the Debye energy is typically much smaller than the Fermi energy because, let's say in aluminum, it's a metal. Fermi energy is huge. It's like 5 millielectron volt. And so this region, which is the region in which this transfer between the two energy of transfer between two electrons is small, is only in these regions where you can have this pairing. But this region of energies are small compared to the Fermi energy. It means that only you can have pairings of electrons that are close to the Fermi energy, close to the Fermi quantum. So here is the energy that is transferred when you have this electron-mediated electron-phonon interaction. So essentially, you have two electrons here. One electron, let's say, with momentum k, and another electron with momentum k prime. So they interact through these phonons, and the electron with, maybe I can do a diagram here. So you have an electron, let's say, with momentum k, and another is coming here with momentum k prime. They interact via the phonon. This is the phonon. And then this gets to k plus q, and this gets into k prime minus q. Okay? And it has to be like that because momentum must be conserved. So the initial momentum k plus k prime have to be the same like k plus q plus k prime minus q. Okay? So during this process, the energy transfer is, it's getting some energy also from the phonons. So the energy transfer, this h bar omega, must be equal to the difference, the energy between the initial and final states for each of the electrons. So it means all these energies must lie close to the Fermi energy because this energy transfer must be inside this window with the Debye frequency. Now you see, you can see, let's say that you have this one electron with the, here with this K1 momentum. And then let's say that you add this Q, and you have two electrons, this with K1 and the other with K2. And then you sum to K1, you sum Q, and to the other one you sum minus Q. you see that if they are in this position, so let's say this is the momentum K1 is of one electron and K2 of the other electron, then this electron is going to be away from this Fermi contour. So this pairing is not going to be favorable, okay? Because you will go into this region in which then the potential becomes repulsive, not attractive, okay? It's just going away from it. So the only way they can actually, you can guarantee that they will, both of them will remain with momentum close to this Fermi surface is if they have opposite momenta, like here, okay? So here one have K1, the other have the opposite, minus K1, which is K2, and if you zoom the K here and minus K here, you see that they are still around in the vicinity of the Fermi contour. So these are actually the electrons that are going to pair, going to form this phase. So this is the condition then. The momenta must be opposite. Any question? Clear? All right, so now we can rewrite, so this effective, and we have this effective interaction here, so particle interaction. Here we have K and K prime in sigma and sigma prime, and now we know that the pairing is going to be between particles with opposite momenta and opposite spin, so we can actually rewrite this in this form here, and I just have shifted the sum. So instead of K plus Q, I will call K plus Q, I will make it equal to K. And it doesn't matter because the sum goes from minus infinity to infinity for the K, so to change K plus Q is the same, okay? So I can rewrite this in this form, and of course this BKK prime is related to BF. I put this 1 over n, and it's the number of particles in there, okay? So if I write this, then I can actually, this is essentially this interaction that is considered in the so-called BCS model of superconductivity. So the BCS theory was introduced in 1957 by John Bardeen, Leon Cooper, and John Robert Schiffer. So that you have the BCS is just from Bardeen, Cooper, Schiffer. And this is a theory that explains conventional, we call it conventional because it's what we know now, superconductivity. So they received the Nobel Prize for this discovery in 1972. And this is essentially the Hamiltonian, the starting Hamiltonian for the BCS theory. Now this is still a complicated Hamiltonian because you have this interaction part here, particle-particle interaction. So we have to simplify it a little bit. So one way of simplifying this is to use the so-called mean field theory. So in the mean field theory, what you do is you essentially neglect fluctuations, okay? So here, let's say that you have two operators, A and B, whatever they are, okay? So the fluctuation of operator A is just the deviation of its value from its average value, right? So the fluctuation of this operator A is just A minus the average of A. And the same for B, okay? So if I multiply these two fluctuations, so I will get this, right? By just multiplying this stuff. And from here I can solve for AB, and you will get this AB. So it gets that you can express the product of two operators as this expression here. Now, if you neglect the fluctuations, so this delta A, delta B, you neglect it, then you can approximate the product of A and B in this form here. What is the idea here? The idea is that you see here in the interaction I have 4 operators in there, okay? I have 4 operators. And I want to simplify this. So if I do that, I will actually have 2 operators combining with average of 2 operators. But the average of 2 operators is just a number. It's not an operator anymore. So I will reduce this interacting Hamiltonian. We have 4 operators because you have electron-electron interaction. into a sort of single particle Hamiltonian, which you have just two operators. Okay. So if I choose A and B in this form, so I will say A is this product of this couple of creation operators, and B is this product of annihilation operator, and I use this formula, this is how I will get. So you see I will get now only these two operators here and two operators, because this is going to be a number, this is going to be a number, and this is also going to be a number. Okay. Now you may say, okay, why you choose A and B in this form? I mean, in principle, I could choose another combination of A and B. Okay. Why I choose this one? Well, this one is the one that leads you to the BCS. You can choose another combination. So actually, there are only three combinations here. One combination will give you Hartree approximation, the other Hartree-Fock approximation, and then this one, which is BCS approximation. Okay. Okay, so when I do this, this is the Hamiltonian I get for my BCS with all these averages. So now I will group all this average here into a couple of functions that I will call delta. Okay? So I will define delta is equal to this. I don't know how much is this average, right? So by now, I will keep it in there. And then I can rewrite the BCS Hamiltonian in this form here. So I have my single particle energy, then this particle here, which is coming from after the mean field approximation, from this interaction, and this from this other interaction. And I have a constant part, which is coming from this product of these two averages here. This is a number, this is a number, so I don't get any operator here. It's just a constant. Okay? So that is the BCS Hamiltonian. I want to find what I want to find. I want to find eventually the spectrum of this Hamiltonian, what are the energies, and I want to find also eventually what are the values of these deltas, because I need to know that. Okay. So for this, one can diagonalize this Hamiltonian using the so-called Bagalyov transformation. Yeah. This delta is a number, okay? It's a complex number in general. It have a.
And this delta is a function of k.
This in general is a function of k. Yes.
That means this delta can also be a function of k plus q.
What is q?
Earlier you showed that k plus q because there is some center of mass moment.
Right, but I absorb this q in the sum. The sum goes from minus infinity to infinity. So you make the sum from minus infinity to infinity over q plus k is just the same. Both of them go from, okay? Infinity plus q is again infinity. Right? So it's absorbed for reading there. All right, so you do this Bagalyov transformation, which consists in introducing this couple of new fermionic operators, these gamma operators here, which are linear combination of electronic operators. So these C are operators that annihilate and create electrons in a given state, and the gammas is a linear combination of them, right? A linear combination which have coefficients this U, V, and the conjugates, okay? All right, so this U and B here cannot be whatever because, well, I want this operator to be fermionic operator, so they must fulfill the fermionic commutation relation. So, and they will actually fulfill, if you make the substitution here, you can find the conditions for which U and B, or the condition that U and B must obey in order for the gamma operators to be fermionic operators. So here is more or less the calculation. This is the commutation relation. Then you substitute gammas, with this expression. You put the gammas in terms of the C, and I know the commutation relation of the C because they are the operators for creation and annihilation of electrons. And then when you find is that then, for this to be equal 1, it means that the square of U plus B squared must be equal 1. Okay, this is a constraint that U and B must obey. Now, in what follow, I will assume that the U and B are real. This is not the most general situation, but this is the easiest one. So in general, they may not be real, okay? For simplicity, I will assume that they are real so that everything is faster and easier. So if they are real, then I can, because the square, you have u squared plus v squared equal 1, I can parameterize them like sine and cosine, because cosine squared plus sine squared equal 1. So I can say, okay, u is just equal to cosine of some angle. Well, we have to find that. And b is equal to the sine of some angle. Okay? So if I say u is equal to this and b is equal to this constraint will be automatically fulfilled. Okay? That is the idea. So I can also, do the inverse transformation and spread the C operators as a function of the gamma operators. And then rewrite my, this Hamiltonian, then I will put all this C as a function of the gamma operators, okay? When you do this, you get these long, terms here, and you can group them, so you get this part, you get this other part. This part have gamma plus and gamma, and this other part have gamma, this will be diagonal. So the term that you have gamma plus gamma are diagonal terms in your Hamiltonian. The terms that have gamma plus, or gamma gamma, these are non-diagonal terms. So in this transformation, what you will do is you will choose u and b in such a way that these terms that have gamma gamma and gamma plus, which are non-diagonal, goes to 0. And then you have diagonalized your Hamiltonian. So it means that I will be choosing my u and b in such a way that this term here and this term here goes to 0. Okay? And this happens when this condition is fulfilled. Okay? This here is actually equal to this here, and it's just this condition here. When this is 0, I end up with only these two terms, and these are diagonal because you have gamma plus gamma, okay? And of course, I still have my constant. This constant is actually the energy of this condensate of Cooper pairs. So when you have the Cooper pairs, they, as was more or less explained in the video, so electrons are fermions, but Cooper pairs are bosons. So this combine, so you see that the total spin is 0 because spin up, spin down. So it's a boson, the Cooper pair. So the Cooper pair then can condensate, and they go to this lower energy state. This is the energy, this ECBS, BCS, is the energy of the condensate. Now, what this equation will describe then, it will describe actually the excitations. What are the states above this condensate energy? So we can rewrite this condition in terms of the sine and cosine that we use to parameterize u and b. And so you get this equation easily. You can use these trigonometric relations and get what the angle is. Cosine of 2 theta k is going to be equal to this expression here. Here, this psi k is the energy, the single particle energy, and delta k is something that still we don't know. We'll figure out what it is. So with this, you can find the eigenvalues, so the values of u and b. And if you make a plot of u and b as a function of k, assuming that this psi k is a parabola, is quadratic dispersion, you will have something like that. So at the Fermi energy, they cross, and then if you have a momentum that is away from the Fermi momentum, then one of them is 0 and the other is not. So essentially, they are describing Hall and particle excitations. So at Kf, the combination, remember these are the coefficients of the linear combinations of electrons and Hall. So you look at the okay, so if you look here at the gamma, so you get gamma, let's say gamma K up is equal to UC, which is destroying an electron, minus B C dagger, which is creating an electron. So you essentially have this linear combination of a destroyed electron, so a hole, and an electron, so a hole and particle. And when these two coefficients are equal, so you get an equal superposition of these electron and hole states. Okay? That's what happened in this picture here at KF. So if you go away from, above KF, so then you get 1 for particles, so it means you have a particle. If you go, the other is 0, and if you go below KF, well below, then you have a hole excitation. Okay, so that is the idea. Now, I can also calculate the spectrum, so I can just go back to this. You look at these steps in these elements here in terms of my cosine. It looks like this, and then now that I calculate the cosine and the sine, I can put it in here and rewrite my Hamiltonian in this diagonal form, in which then you can put this EK, which is the spectrum of the excitations of the BCS Hamiltonian. So again, this part describes the condensate energy, and this part creates the excitations. So you make the plot of this excitation, this is what you will get. Okay, so the plot of this EK, you just will get this. If delta is equal to 0, you will get 0 here. If delta is not 0, you will open this gap. So this gap is equal to this delta. So what is the meaning of delta? Delta is the thing that is protecting the condensate. Okay? So the condensates have 0 energy. So, or this condensate energy, EBCS is the condensate energy. I will put this to 0, yes, it will be my reference energy, the 0 of my energy scale. So the condensate have this energy, 0, okay? Now, if there is no delta, whatever small energy that I can get will give me transition from this condensate into this hole or particle electron states. So I won't see any superconductivity because this condensate won't be stable. Any minimal amount of energy just will break these Cooper pairs, okay? Now, if I have some finite delta, the situation is different because then I will have to pay this energy, delta, to destroy this Cooper pair. So I will have to pay this energy to make a transition from the energy of the Cooper pairs into an energy of this excitation here, okay? So delta is essentially the energy that you will need to pay to break the Cooper pairs. Is the energy that is protecting your superconductivity. Is you calculate how much is this energy in this low temperature or conventional superconductivity, is just typically a few millielectron volts, which when you convert it to temperature, then you see that they have to be like these few kelvins. Okay. So I think we'll take a break now. Right.